Lecture 10. We're going to deal with two problems today. One is a more advanced version of Lagrangian mechanics called method of Lagrange Multipliers, and the idea there is that you can access constraint forces. I'll talk a little bit more about that in a moment. And then in the second half, what I'm going to do is look at conservation of momentum and energy from the perspective of Lagrangian mechanics, and that'll bring us to something we call Noether's theorem. So, Lagrange multipliers. We've spent the last few lectures doing Lagrangian mechanics, and one of the really nice features of Lagrangian mechanics is that you can kind of bypass forces of constraint. So things like tension in a string for a pendulum, normal force on surfaces, kind of don't appear in the problem, and it enables you to make things a lot easier in many cases. But sometimes you do want to know what the constraint forces are, because they're important to the way you design things. So to give one example, you might have a pendulum. You have a very big mass, for example, connected to a metal cable or a rod, and if you don't know what the tension force in this rod is, then you don't know what mechanical strength this has to be in order for it to not to snap under load. Okay, so sometimes you actually do want to access these forces, and you still want to be able to use Lagrangian mechanics because it might be convenient for a particular problem, but still get access to that forces. And the way that we can do that is a method known as the method of Lagrange multipliers, which we're going to talk about today. And so the way we're going to set this up is we're going to start out just with a simple system like a pendulum, build up the method itself in terms of the mathematics, and then we'll quickly at the end do two problems that highlight how this problem or how this approach turns out the constraint force that we see. Okay, so let's go back to our really familiar problem of pendulum to work with here. So, seen this a few times before now. We've got a mass m connected to a pivot point via a string of length L, and there's an angle in here, phi, and usually for most of these problems we set up our coordinate system so that we have y pointing downwards to make things nice and easy in terms of the coordinates, okay? And you'll remember back when we were talking about constraint forces, we basically had this thing called a constraint equation that connected some of the parameters to something that defines the constraint, okay? In the case of our pendulum, what we do is we basically say that our coordinates x and y are constrained such that they maintain the length L of the rod or string in the pendulum, okay? So we can start out with that directly because we remember that from a little while ago. It's basically square root of x squared plus y squared equals L, okay? And what we're going to do here is build up a version of Lagrangian mechanics that basically enables us to access that constraint force F, okay, in here. Right. So in this particular case, we've got two coordinates x and y, and you'll notice last time we basically used the constraint to reduce down to one coordinate, which was phi. But what we're going to do here in this method is actually keep both of our coordinates, because we're not going to use the constraint force to eliminate one, okay? So we're going to work in x and y rather than phi. And that means we're going to have a Lagrangian, and we can work out what that's going to be later on. It's going to be x and x dot, y and y dot, okay? So it's going to be a function of 4 different parameters in here. It could be a function of t as well, but in this particular case it's not, okay? There's no energy dependent terms. There's no time dependent terms in either the kinetic energy or the potential energy. Okay, so where we're going to start here is with Hamilton's principle. And it basically says that we have some action S that's integral between t1 and t2, and this could be any time t1 and t2 in the motion of the pendulum, where we take the integral of x, Lagrangian of x, which is a function of x, x dot, y, and y dot, okay, dt. And the key idea of Hamilton's principle is that this thing is stationary, okay? And so again, we're going to take a similar approach to what we have before of having right paths and wrong paths, right? And what we're going to do is denote our right path as x of t and y of t, okay? So basically we're just going to let those two coordinates evolve as a function of time, and by mapping the two together against time, we know what the right path of the system is, okay? It's just going to be what's held to in the constraints. And then we're going to imagine a small displacement to a neighboring wrong path. And at the moment, that's going to seem a little weird because it's going to be like the motion's constrained. How can you go to a wrong path? What we're actually going to do here is basically tie Hamilton's principle in with the constraint force by essentially temporarily relaxing the constraints. So we have a wrong path. And it's going to be x of t plus, whoops, I need a plus, not an equals, plus delta x of t. So we're just going to add a little something to make the path a little bit wrong, and y of t will do likewise, plus delta y of t. Okay? And then, provided that the everything behaves itself in terms of the constraint equation and Hamilton's principle, we know that delta x and delta y are going to be 0, right? And basically what we can say in here is that ultimately we're looking for delta s equals 0. Whoops. Delta s equals 0 obeys our Hamilton's principle, okay? So that's ultimately what we're looking for. So what we need to do in here is write an equation in delta s in terms of the displacements in the other directions, okay? And this is fairly easily done, just going back to what we know from calculus. So this will now be integral, and I'll leave the 2 times off here just to keep things simple. It's going to be dl on dx delta x plus dl on dx dot dx delta x dot plus dl on dy delta y plus dl on dy dot delta y dot. And I just need to go through here and clean that one up. Sometimes I get my deltas and my del's mixed up. Okay, like so, dt, okay? And so all we're really saying here is that we can vary s, and s of course is an integral of L. We can vary s by varying L in 4 different ways. We can change x, we can change x dot, we can change y, and we can change y dot, and all of those can be possible contributors to that change, okay? So this is just a typical expression that you would have from sort of a real analysis course in here. The trick we're going to pull in here, and I'm not going to go into it in a lot of detail because we've done it in some past lectures, is we're going to use integration by parts on the second and the fourth terms in here, okay? And we're going to use the form that we've dealt with before. That looks a little bit like uv dash, sorry, it's u dash v. U dash v dx is equal to minus uv dash dx, relying on a definite term for uv being 0. Okay, and remember that all the way through calculus of variations and Lagrangian mechanics, we've always been able to take this definite term to be 0 because the 2 endpoints have to be common between the right and wrong paths, okay? If you're not familiar with that, you should go back a lecture or 2. Okay, so really what we can do here is just swap the derivative on the 2 terms and invoke a minus sign in here. It's a really nice aspect of our integration by parts. And so just to highlight what it's going to look like for the second term, what we would have is dl on dx dot delta x dot dt would become minus integral yeah, okay, this is good. What am I doing here? Oh yeah, of course. I'm taking d on dt of dl on dx dot delta x dt. Okay, so even I had to remind myself exactly what I was doing just then. So what I'm doing here is I'm treating this term here as my u. So it's u dash on the left-hand side, and it then becomes u on the right, so we're taking the derivative away from that term, and then we're treating this one as my v, and it becomes v dash over here on the right-hand side, and of course we take the time derivative of that, but if I just sling a dot on the top, it's a bit confusing, so I'm going to leave it as d on dt. Okay, so that's exactly what I've done there, just so it's really clear. And we can do the same thing for y, right? You could write an equivalent expression. So now what we can do in here is go delta s is equal to integral. And what I'm going to do, just to keep things nice and tight, is cluster the first and second term and cluster the third and fourth term, just to keep things simple in here straight up. So this will be dl on dx, and you'll notice that there's a delta x up there that I'm going to carry out to the end in a second, and there's a corresponding delta x just here now, okay, which is the one I'm going to pull out the end as well. So this is going to be minus, wrong color, minus d on dt, dl on dx dot delta x. Okay, so all I've done is just put the minus sign in doing the integration by parts, and then carry the delta x out the end, dt, plus a second integral. And you remember that I can take an integral with two terms inside and turn it into two separate integrals, right? Sum of two integrals is the integral of the sum. So this is now dl on dy minus d on dt, dl on dy dot, and again I can take this delta y outside dt, okay? And you've probably already spotted where I'm heading here, because you'll start to see an Euler-Lagrange equation popping up in here. Sure enough, I'm interested in building one of these, right? So I've basically not done anything terribly special yet, except to get myself back into a strategic position where I'm going to pull out something that looks like an Euler-Lagrange equation, okay? And of course, if there's no constraints, this thing just becomes the Euler-Lagrange equation, right? It just collapses back to a fairly simple result. And of course, let me just finish this bit off here for a second. Of course, this whole thing equals 0, and let's call this equation 1 just so we can track it further down. Okay, so if we've got constraints, we go with a slightly different procedure here, right? So since all points concerned with a particular constraint equation satisfy basically f of x of y equals a constant, right? Because that's our constraint equation. Then if we make a displacement, we maintain the constraint equation, okay? So what we're really saying here is that f of x and y is equal to a constant. And if that's true, then delta f has to be equal to 0, right? Because otherwise f is not going to be constant. And we can write delta f, again, from a calculus perspective, as a change in f on, with respect to x, delta x, plus df on dy delta y, okay? And of course, this thing is equal to 0, right? So all I've done here is, instead of go and say my action has to be 0 and these two terms have to turn out to be 0 and pop out Euler-Lagrange equations, I've said I'm going to stop here for a second. I'm going to have a look at something that my constraint equation will give me. And because my constraint equation basically says that, you know, some function of x and y is a constant, I know that that thing can't change, and I can build a a little function out of this, okay? All right, so since this thing here is 0, what we can do is we can multiply it by an arbitrary function, and we can add it to our equation 1. And what we're really doing here is taking 0, multiplying it by an arbitrary function, so it's kind of still 0, and adding it into something which is just adding 0 on, okay? And so what we have here is a function that we call lambda t, and for the moment it's arbitrary, it can be anything we like. Later on it'll actually turn out to be connected to our constraint force, okay? And we call this thing a Lagrange multiplier, okay? And it's really just that we're multiplying something by something, so that's where the multiplier comes from, and Lagrange just from the origin of the system of equations we're dealing with, okay? So what we can do in here is basically take this equation here, multiply it by lambda of t, and then add it into 1, right? So we're really just adding 0 to something, so it shouldn't change. And so what we would have here is delta s, and the way I'm going to add this in is I'm going to split the two terms onto the two sides, okay? So this would be integral dl on dx. I'm going to shove it in the middle, so this is plus lambda of t df on dx minus d on dt dl on dx dot delta x dt, and it's a little bit short on space here, so let's add the second term down here. We're going to have a similar one in y, dl on dy plus lambda of t df on dy minus d on dt dl on dy dot delta y dt. And of course this thing is going to stay equal to 0 because I took something that was equal to 0 and I added something that was equal to 0 to it, okay? At this point it's like, okay, we're going somewhere, let's see where we're going. But there's some inspired genius behind this whole thing, and here's the clever bit. What we can do in here is basically arrange for the coefficient for dx here in this first integral. Let me just change in color again. So this is like a coefficient for delta x in here, okay? And we know that from earlier work on calculus of variations, that basically what's going to happen is this thing here is going to turn out to be equal to 0, right? And that's going to carry the same way into this second equation. So these two big equations that we've got here are now equal to 0. And so this is where the really clever bit about this approach comes from. We've basically taken an approach that exists already, and what we've done is taken something that we can treat as 0 and add it in, and then rely on that thing being 0 so that we can now pull it out as a set of equations, okay? So what this means basically is that we can arrange for dl on dx plus lambda of t df on dx minus d on dt dl on dx dot to be 0. Or another way to write this is as dl on dx plus lambda of t df on dx is equal to d on dt dl on dx dot. And there would be an equivalent equation for y, okay? And so now that we've done this, you're probably seeing a little bit of what's going on in here, okay? So what we've basically done is add a term that effectively is equal to 0 into an equation to get another term in there, right? And what we're going to do in here in the end is use this approach in here to get us this function lambda of t that's then going to be connected to our constraint force, right? And as you know, in any particular problem, that constraint force is not a real force in the sense that it's acted, you know, it's by anything externally. It basically exists because of Newton's third law, right? Which, you know, for every force, there's an equal and opposite corresponding force. And so that basically gives you two terms that add together to 0, right? And that's more or less what we're doing here. So we're sort of invoking Newton's third law in some ways into Lagrangian mechanics in order to get access to what that constraint force is. What you'll notice is that we now have two Lagrange equations. Let me get rid of the circle so it's not confusing. We've got two Lagrange equations and two unknowns. It's always hard at the start of the week trying to find your groove again. It's probably easy if you work through the series to work through which are my first lectures of the week. So x of t and y of t. And normally that's what we would have, right? If we were not ignoring our constraint force here, we would have two equations, two unknowns, and work from there. What we do in this approach now is that we have also a constraint equation, and we have lambda of t as an unknown. And so really all we're doing here is just adding one more equation and one more unknown to our system so that we can access a little bit more information in the system, okay? So let's take this. All we've really done, if we work back through our logic here, is do the same thing that we've done in the past to set ourselves up with Hamilton's principle to get Euler-Lagrange equations. And we've really just taken a requirement from the constraints to add something that's, you know, a function times 0 onto something, and then use that as a way to then add, just slip that unknown into the equation. We have an additional equation, which is the constraint equation, which allows us to get something, right? And I guess that kind of hits at what's really clever about the Lagrange multipliers approach. We've used a 0 to sneak an extra unknown in off the back of another equation so that we can then solve out what the constraint force is, despite the fact that it doesn't turn up in the method normally, okay? And so it just appears as an additional term in here that when we go to solve this thing, we can access what we're looking for, okay? All right, so let's see if we can put some meaning to this thing for a moment. Let's take a Lagrangian, and we'll treat it as kind of a generic Lagrangian for a moment. So it'd be something like a half mx dot squared plus a half my dot squared minus u of x and y. And you'll notice that I started out with a pendulum, which is perfectly okay. And now I've written something a bit more generic because I'm trying to catch a bit more space around this. But you can write the Lagrangian for the pendulum in exactly the same way I've got here, right? You would then put in a potential term, which would be your gravitational potential energy, and you'd have a specific Hamiltonian for that particular system, okay? If you take this Lagrangian here, and let's for a moment call this equation 2, and you can assume that there's an equation 3, which is the y version of it. And you can try this for yourself later on. What we can do is take this Lagrangian and insert it into equation 2. So what we're going to do here is we're going to need some derivatives. First, we're going to need dl on dx. And of course, it's going to be the only term in here that's got an x dependence is u. So we're going to get essentially minus du on dx. Okay, and we know from a lot of our earlier work in the course that this is just a force, but we'll come back to that in a second. We also need dl on dx dot, and we know that that comes from our kinetic energy term just in here. There's no terms like that in the potential because we're dealing with a conservative system. And so that's going to give us mx dot. And so when we write our new Lagrange equation for 2, what we've got is minus du on dx plus lambda df on dx is equal to d on dt of mx dot, and we know this is just mx double dot, right? Normally in our notation, okay? And so let's think about this for a second. This is the x component of our non-constraint force, right? Because, oops, trying to think and write at the same time doesn't work very well. Okay, so this is just the x component of our non-constraint force, because you'll notice that when we write the potential, we relate it to forces that are not constraint forces, right? In this particular case, for the pendulum, it's gravity, and our tension in the string doesn't turn anywhere up in the potential, right? It's a separate kind of force that doesn't exist inside potentials. And then this term here is the total or net force on the system, okay? And then this term in here that's hanging around in the middle, this ends up being the x component of the constraint force. We've just added in an extra little term in here, okay? And so what we can write this as is fx constraint is equal to lambda df on dx, and we would get a similar one for y. Okay, so all I've really done here in the end is done a little bit of a mathematical trick to add an extra term into my Euler-Lagrange equation that basically just corresponds to the x component or the y component or the whatever direction component you're dealing with in your particular Euler-Lagrange equation of the constraint force, okay? And really I'm relying on the fact that if you consider the whole system, essentially these constraint forces kind of cancel each other out in a way to 0, and we can kind of just bootstrap them back into the equation via a 0. Okay, that's sort of the magic in the maths here. At this point, things might look a little like, what the hell did you just do? This doesn't make any sense. So what I'm going to do is plug through quickly on 2 different problems here and demonstrate how we actually pull out our 2 constraint forces. Okay, so this brings me to a problem that I like to call Atwood's revenge, which is basically we go back to the Atwood's pulley problem that we did in the last lecture, but now we're going to do it with a Lagrange multiplier approach and basically just demonstrate that the tension in the string pops out of what we have here. Okay, so let's go through here and do it. So we're going to pull back the Lagrangian that we had earlier from this problem because I don't want to redo the whole thing again. So our Lagrangian is a half m1 x dot squared plus a half m2 y dot squared plus m1g x plus m2g y. Okay, and you'll remember when we did this problem we had a constraint equation. F of x and y is x plus y equals a constant. Okay, so really all we did was say that we have x, we've got the bit around the top of the pulley, which we can just put into the constant, and y, and that length of string has to be fixed, okay? And what we did when we solved this last time was we basically used the constraint equation to eliminate one of the variables so that we had 1 degree of freedom in the problem, which is basically the system moving about the rotation of the pulley, and one variable, which is just where something is in this thing, right? What we're going to do here is we're going to keep the extra variable in here. We're going to keep the extra variable in here so that we can keep the constraint equation and use that to get us the force as a constraint out, okay? All right, so what we got here is struggling to even spell today. Two modified Lagrange equations. You know, you're getting fairly well into a very, very long term of writing lectures and recording lectures when even a can of Red Bull just won't start you up in the morning. Okay, so we've got two modified Lagrange equations. They're the ones that we just did, okay? So the first one is in x, and it's dl on dx plus lambda df on dx equals d on dt dl on dx dot, okay? And we can go through, I'm going to go a bit faster this time, so we know that our dl on dx is just m1g, okay, so we're just pulling down the term that's related to x in here, plus lambda times, if we take our derivative of df, of f of x of y, let's write the two derivatives over here. Df on dx is just going to be x, actually it's just going to be 1, right? Because we're taking derivative of x, so it's just going to be 1, go to green, 1. And df on dy is also just going to be 1, okay? So what we're going to end up here with is lambda times 1 is equal to m1x dot, and because this just comes down from this thing up here, and then when we take the time derivative of it, we get our second dot, so we've got this, okay? So let's number these equations. This is number 1, our constraint equation. This is number 2, our first Lagrange equation, okay? And we can just write this as m1g plus lambda is equal to m1x double dot. And then we got the same, exactly the same thing in y. So dl on dy plus lambda df on dy is equal to d on dt dl on dy dot, okay? And so this thing will pop out as, we'll get an m2g here, plus lambda times 1 is just lambda is equal to m2y double dot, with the y dot coming from this term in here, and the second dot coming from the d on dt that's in the Lagrange equation just here, okay? All right, and so we call this one number 3, okay? So now we've done the same problem we did in the last lecture, where we basically had one unknown and one Lagrange equation, and now what we've done is got 3 equations, 3 unknowns, and we're going to work through and solve this thing out, right? So we can take one, and now we're just into equation grinding, basically. So we've got y equals a constant minus x here. We can take the time derivative of both sides, so what we'll have is y dot is equal to minus x dot. And we can take the derivative of both sides again, and what we've got is y double dot is equal to minus x double dot, okay? And let's call this 4 for the moment, just to keep track of this. And then what we can do is take equation 2 minus equation 3. And this is, again, kind of an inspired thing. I know what the solution looked like in the last lecture, and if you want, you can stop at this point and go back and remind yourself what it looked like and why I'm going the direction I'm going. I'm going to subtract these 2 equations, because what I'm going to get is m1 minus m2g is equal to m1x double dot minus m2y double dot. And then, of course, I know that y double dot is equal to minus x double dot. So this is going to be m1x double dot plus m2x double dot. In a sense, I'm using the constraint equation here. And this is going to be m1 plus m2x double dot. Just there. And then I can solve this thing for x double dot. So I've got x double dot is m1 minus m2 g on m1 plus m2. And that's exactly the same solution that I had last time, right? And then I can in principle do the same thing for y. And I'll let you do this one for yourself just to save some time here. This thing is going to end up being m2 minus m1 g on m1 plus m2, okay? Okay, so they're what I got in lecture 9. And now the last step of this is I want to get lambda, right? And so I can finish this by now basically taking my equations 2 and 3 up here and basically just isolating out my lambdas, okay? So, let's finish with lambda. Our equation 2 becomes lambda equals m1x double dot minus m1g. And 3 here becomes lambda equals m2y double dot minus m2g. Okay? And if you think about this in terms of a first year problem, this is really just the tension on the string popping out, right? What we've got is net force minus the gravitational force is going to correspond to the tension in the string on both of the two sides. You'll have seen exactly this problem in first year. And so this is the nice thing here. We've basically just built a little bit of architecture into our Lagrange method in order to pop ourselves out tensions. Okay, to finish off, I'm just going to come back around, close the loop, because I kind of started by doing pendulum problem, and you could almost say I sort of went off on a tangent and got a general result and never really came back and closed the loop on the pendulum. Okay, so I want to come back and just finish that one off kind of quickly here. So let's come back to our original problem. What we've got is mass on a string again, length L, angle phi in here, set up our coordinate system, x and y, and this time I'm actually going to care a little bit about y. So my y starts here at the pivot point, and so this point here I'm going to call y, and I'm going to be able to track the y of the bob at any particular point in time as a function of x if I wanted to. And then I know that this distance down here is L, so this little height in here is actually L minus y. And I just want to point out something kind of important here for Lagrange multiplier problems. If you go back to one of the previous lectures where I've done the pendulum using the Lagrange method, what I've done is I've slipped directly across to using phi as my coordinate because I have 1 degree of freedom, and then the one coordinate that remains after the constraints is that angle phi, right? And so I've got a potential energy that's in terms of phi and worked my way from there, right? When you do the Lagrange multipliers method, you've got to not do that. There's a different path through this, and if I start to write terms in phi in this problem, what I'm going to do is end up having to get the phi's back out again, right? So number one rule with Lagrange multipliers method, try to stay in the coordinates that are connected to your constraint force because the problem will be a lot easier, okay? So we're going to write our Lagrangian now, but unlike last time where we wrote it in terms of, or tried to get it in terms of phi, now we're going to keep it in x and y, right? So this will be a half m x dot squared plus y dot squared minus mg, and then our height down here is L minus y, okay? And then we've got our constraint equation, f of x and y is square root x squared plus y squared is equal to L, okay? And so the approach is kind of simple in here. We've got our two modified Lagrange equations. And so let's deal with them one by one. The first one is dl on dx plus lambda df on dx equals d on dt dl on dx dot. Okay. So in here, this is going to be 0, and it's going to be 0 because there's no terms in x in the Lagrangian. This is going to be our usual mx dot, and then when we take the time derivative, we'll get mx double dot. Lambda in here is lambda, it's fine. And then df on dx in here is going to be the derivative with respect to x of this thing, right? And so it is just x on square root x squared plus y squared. I'll let you confirm that for yourself, okay? I'm going to jump straight over that step. So this is going to be lambda x on square root x squared plus y squared is equal to mx double dot. And of course, x squared plus y squared is just L. So we could write this as lambda x on L is equal to mx double dot. And let's call this equation 1, okay? All right, for the second one, everything is going to be similar in terms of this overall equation at the top. So I'm going to save myself time and not write it again. But I can work out what the various components are going to be, right? So first I need dl on dy. And when I take dl on dy, what I'm doing is taking, this will become minus mgl plus mgy. And so when I take the derivative with respect to y, I'm going to get an mg, okay? So there'll be an mg in here plus lambda. Now my df on dy will be y on square root x squared plus y squared, okay? So I'm taking the derivative with respect to the other variable here. Will be equal to my double dot. And I can pull the same little bit of geometry that I just had in here and go mg plus lambda y on L is equal to my double dot, just here. Okay, so call that equation 2. And then I can deal with my constraint. And I'm going to do things very tiny differently here. Rather than just go, I've got a lambda, I need to work out what lambda is. I know what lambda is, right? I know that it's the tension in the rod. So I can just call this the tension in the rod straight up. Okay, so I'm just going to call this f of t, tension in the rod. And I'm going to use lambda to get me this thing, right? Okay, so what I know is that the tension, let me just put the t up the top so I can keep my components happy. ft, not down there. So f of t of x, so just the x component here, I can pull out just using my Lagrange multiplier, right? So it's going to be lambda df on dx. And we worked that out above. It's going to be f of t, or actually let's just call it lambda for now, just to keep it sensible. This is going to be lambda, and we know that it's x on square root of x squared plus y squared, right? We took that derivative just up here. So it's going to be x on L. And if we go back up to our diagram up here, we know that x on L is going to be sine of phi, right? So this is just going to be lambda sine phi. And he writes theta. I'm having one of those days. So this is number 3. And then for y, we can do the same thing, right? F of t of y is equal to lambda df on dy is equal to lambda y on L. And of course, it's going to be the other component in the triangle, so it's going to be cos phi in here. We can call this 4, okay? All right. Okay, so at this point, what we can do is basically substitute 3 into 1, right? In other words, we use the knowledge that we got from 3 in 1. And what that really is that we know that lambda x on L is equal to f of t of x, and we can substitute it in where this is, right? So all we're going to do here is basically go that f t x is equal to mx double dot. And basically all we're saying is that the x component of the tension in the string can only come about from the acceleration of the bob, okay? And so that ultimately we know that tension is going to change as a function of position because that component's going to change. We can also put what we know from 4 into 2, and this will give us something a little bit more sensible. What we've got is mg plus, and again here what we're going to do is go that this thing here is this thing here, so we can basically put f of t of y into there. So this is f t y is my double dot. And then if we clean this thing up, we know that f t y is equal to m y double dot minus g. Okay, and so all we're saying here is that we've got a total, and remember y is pointing downwards, we've got a total a force or acceleration down on this rod, and if we subtract the component that comes from gravity, we get the piece that's connected to the tension in the rod. Okay, right, that's all we've done. Solve both problems. So fairly straightforward. All we've really done in this is basically take our usual Lagrange approach, add a little component that we can essentially treat as 0 to bring in our constraint force, and then as long as we stay in the right coordinate system to solve the 3 equations that pop out, which is the n+1 equations that would pop out, one of them being the constraint force, the other ones being the Euler Lagrange equations, we can basically solve out, and in addition to solving the problems via the same approach we'd normally use, we can get the constraint forces as well. Okay, it's a really useful thing to have. So I think we'll take a break here, and then we'll come back and deal with conservation forces in the Lagrange approach.